It is important to remain calm when you are blamed for something that is not your fault. Explain the situation clearly and calmly. Let the person know that you're not responsible for the problem and explain what you have done to investigate it. If you can, offer to help the person find a solution to the problem. This shows that you're willing to be helpful and that you're not just trying to pass the buck. If possible, document your findings so that you have proof that you're not responsible for the problem. This could include taking pictures, writing down notes, or getting a statement from a witness. It's also important to remember that sometimes people will simply refuse to believe that you're not responsible for a problem. In these cases, it's best to move on and focus on finding a solution. When dealing with electrical circuits and potential overloads, there are several key concepts and steps to consider. These are essential for understanding the situation and finding a resolution. Firstly, understanding circuit loading is critical. Every electrical circuit is designed to handle a specific amount of current, measured in amps. This limit is determined by the circuit breaker protecting the circuit and the wire gauge used in the wiring. Overloading a circuit means drawing more current than it is designed to handle, which can cause the breaker to trip, and in severe cases create a fire hazard. Secondly, identifying the load on the circuit is vital. To determine if a circuit is overloaded, you need to calculate the total current being drawn by all the devices connected to it. This involves looking at the nameplate on each device to find its power consumption in watts or amps. If the power consumption is listed in watts, you can convert it to amps using the formula amps equals watts divided by volts. In the United States, the standard voltage for most residential and commercial circuits is 120 volts. Thirdly, the next thing to do is to check the breaker rating. The circuit breaker's rating indicates the maximum current it can handle before tripping. Common breaker sizes are 15 amps, 20 amps, and 30 amps. The breaker should be clearly labeled with its amperage rating. Then calculate the total current. Add up the amperage of all devices connected to the circuit. For example, if you have 3 computers each drawing 2 amps, 2 monitors each drawing 2.5 amps, and a printer drawing 1 amp, the total current would be 3 times 2 amps plus 2 times 2.5 amps plus 1 amp, which equals 12 amps. Comparing the total current to the breaker rating is the next step. If the total current exceeds the breaker rating, the circuit is overloaded. In the example above, if the circuit breaker is rated at 15 amps and the total current draw is 12 amps, the circuit is not overloaded. However, it is nearing its maximum capacity, and adding more devices could cause it to trip. But if the breaker is rated at 20 amps and is tripping, there is another problem that needs to be investigated. Next, investigate the appliances and devices. Some devices, particularly those with motors or heating elements, draw more current when they first start up. This is known as inrush current. If several devices with high inrush current start simultaneously, they can temporarily overload the circuit and cause the breaker to trip. Then consider the type of devices. High-power devices like space heaters, hair dryers, and power tools draw a significant amount of current. Connecting multiple high-power devices to the same circuit is a common cause of overloads. If a circuit breaker trips frequently, it may be a sign of a problem with the breaker itself. Breakers can weaken over time and trip at lower current levels than their rating. A qualified electrician can test the breaker to ensure it is functioning correctly. The next thing to consider is the wiring. The wire gauge used in the circuit must be appropriate for the breaker size. Using too small of a wire gauge can cause the wire to overheat, creating a fire hazard. The National Electrical Code, or NEC, specifies the appropriate wire gauge for different breaker sizes and circuit types. When dealing with any electrical issues, safety should always be the top priority. If you are not comfortable working with electricity, it is best to call a qualified electrician. Working with electricity can be dangerous and can result in serious injury or even death. Here are several common causes of circuit overloads. 1. Too many devices on one circuit. Connecting too many devices to a single circuit is the most common cause of overloads. Each circuit has a maximum current it can safely carry, and exceeding this limit will cause the breaker to trip. 2. High power devices. Appliances and devices that draw a lot of power, such as space heaters, microwave ovens, and power tools, can easily overload the circuit, especially if other devices are already connected to it. 3. Inrush current. Some devices, particularly those with motors, draw a large amount of current when they first start up. This inrush current can briefly exceed the circuit's capacity and cause the breaker to trip. 4. Damaged wiring. Damaged or deteriorated wiring can increase the resistance in the circuit, causing it to overheat and trip the breaker. 5. Loose connections. Loose connections can also cause increased resistance and heat, leading to an overload. 6. Faulty appliances. A malfunctioning appliance can draw excessive current and overload the circuit. 7. Shared neutral wires. In some older electrical systems, multiple circuits may share a common neutral wire. If the load on these circuits is not balanced, the neutral wire can become overloaded, even if the individual circuits are not. 8. Incorrect breaker size. Using a breaker that is too large for the wiring can allow the circuit to be overloaded without tripping, creating a fire hazard. 9. Multi-wire branch circuits. These circuits share a neutral conductor between two hot conductors. If the loads on the two hot conductors are not balanced, the neutral conductor can become overloaded. 10. Extension cords. Using extension cords, especially multiple extension cords plugged into each other, can reduce the current carrying capacity of the circuit and lead to overloads. Extension cords are typically not rated for the same amperage as the wall circuits. Here are some steps for troubleshooting an overloaded circuit. Firstly, identify the affected circuit. When a breaker trips, the first step is to identify which circuit is affected. Check the breaker panel to see which breaker has tripped. It will usually be in the off position or in the center position between on and off. Secondly, reduce the load. Disconnect some of the devices on the circuit. Start with high-power devices or those that are not essential. Thirdly, reset the breaker. Flip the breaker to the off position and then back to the on position. If the breaker trips immediately, there is still an overload or a short circuit. Fourthly, test the circuit. Plug in the devices one at a time to see if any particular device causes the breaker to trip. If a device causes the breaker to trip, it may be faulty or draw too much current. Fifthly, check the wiring. Inspect the wiring for any signs of damage, such as frayed insulation or loose connections. If you find any damage, have it repaired by a qualified electrician. Sixthly, use a circuit analyzer. A circuit analyzer can measure the voltage, current, and impedance of the circuit. This can help identify problems such as overloads, short circuits, and ground faults. Seventhly, balance the load. If you have multiple circuits in your home or office, try to balance the load between them. This means distributing the devices so that no single circuit is overloaded. Eighthly, upgrade the wiring. If you frequently experience overloaded circuits, you may need to upgrade the wiring. This may involve replacing the existing wiring with a larger gauge wire or adding new circuits. Ninthly, use power strips with overload protection. These power strips have a built-in circuit breaker that will trip if the current exceeds a certain level. Tenthly, call an electrician. If you are not comfortable working with electricity or if you are unable to resolve the problem, call a qualified electrician. Here are some best practices for preventing circuit overloads. Firstly, use the correct size breaker. Make sure that the breaker is the correct size for the wiring. Using a breaker that is too large can allow the circuit to be overloaded without tripping, creating a fire hazard. Secondly, use the correct gauge wire. Use the correct gauge wire for the breaker size and the circuit type. The NEC specifies the appropriate wire gauge for different applications. Thirdly, avoid overloading circuits. Avoid connecting too many devices to a single circuit. Use multiple circuits to distribute the load. Fourthly, use high-efficiency appliances. Use high-efficiency appliances and devices that draw less power. Fifthly, unplug unused devices. Unplug devices that are not in use to reduce the overall load on the circuit. Sixthly, use power management software. Use power management software on computers and other devices to reduce their power consumption when they are not in use. Seventhly, inspect wiring regularly. Inspect wiring regularly for any signs of damage or deterioration. Eighthly, avoid using extension cords. Avoid using extension cords, especially multiple extension cords plugged into each other. If you must use an extension cord, make sure it is rated for the appropriate amperage. Ninthly, install dedicated circuits. Install dedicated circuits for high-power devices such as space heaters, microwave ovens, and refrigerators. Tenthly, educate yourself. Educate yourself about electrical safety and the proper use of electrical devices. When adding new circuits, several factors must be considered to ensure safety and compliance with electrical codes. Firstly, assess the need for the new circuit. Determine why the new circuit is needed. Is it to accommodate additional appliances, relieve an overloaded circuit, or provide power to a new area? Understanding the purpose of the new circuit will help determine its specifications. Secondly, calculate the load requirements. Calculate the total load that the new circuit will need to support. This involves adding up the amperage of all devices that will be connected to the circuit. Remember to account for inrush current for devices with motors or heating elements. Thirdly, determine the appropriate breaker size. Select a breaker size that is appropriate for the load and the wire gauge. The NEC provides guidelines for determining the appropriate breaker size. For example, a 15 amp circuit typically requires 14 gauge wire, while a 20 amp circuit requires 12 gauge wire. Fourthly, choose the correct wire gauge. Choose a wire gauge that is appropriate for the breaker size and the circuit type. The NEC specifies the allowable ampacity for different wire gauges and insulation types. Using too small of a wire gauge can cause the wire to overheat and create a fire hazard. Fifthly, select the appropriate cable type. Select the appropriate cable type for the application. Common cable types include non-metallic sheet cable or NM cable, also known as Romex, which is typically used for residential wiring, and conduit, which is used for commercial and industrial wiring. Sixthly, plan the circuit layout. Plan the layout of the circuit, including the location of receptacles, switches, and lighting fixtures. Ensure that the layout complies with local electrical codes. Seventhly, install the wiring. Install the wiring according to the NEC and local electrical codes. This includes properly securing the cable, making proper connections, and grounding the circuit. Eighthly, install the breaker. Install the breaker in the electrical panel. Make sure that the breaker is properly sized and labeled. Ninthly, test the circuit. Test the circuit to ensure that it is working properly. This includes checking the voltage, current, and polarity. Tenthly, obtain necessary permits and inspections. Obtain any necessary permits and inspections from the local building department. This will ensure that the new circuit complies with all applicable codes and regulations. When dealing with older electrical systems, several unique challenges and considerations must be taken into account. Firstly, wiring insulation. Older wiring may have deteriorated insulation, which can create a fire hazard. The insulation may become brittle and crack, exposing the bare wire. This can lead to short circuits and ground faults. Secondly, insufficient grounding. Older electrical systems may not have adequate grounding, which can increase the risk of electric shock. Grounding provides a path for fault current to flow back to the source, tripping the breaker and preventing a shock. Thirdly, outdated wiring methods. Older wiring methods may not meet current safety standards. For example, some older homes may still have knob and tube wiring, which is considered obsolete and potentially dangerous. Fourthly, undersized service panels. Older homes may have undersized service panels that cannot handle the electrical demands of modern appliances and devices. This can lead to overloaded circuits and frequent breaker trips. Fifthly, lack of arc fault circuit interrupters, or SIs. SIs are designed to detect arc faults, which are a common cause of electrical fires. Older electrical systems may not have SIs, increasing the risk of fire. Sixthly, shared neutral wires. Older electrical systems may have shared neutral wires, which can become overloaded if the load on the circuits is not balanced. Seventhly, aluminum wiring. Some homes built in the 1960s and 1970s have aluminum wiring, which can become loose and corroded over time, creating a fire hazard. Eighthly, two-wire systems. Some older homes may have two-wire systems without a grounding conductor. This can increase the risk of electric shock. Ninthly, asbestos. Some older electrical equipment, such as wiring, insulation, and panel boards, may contain asbestos, which is a hazardous material. Tenthly, code compliance. Older electrical systems may not comply with current electrical codes. This can create safety hazards and make it difficult to obtain insurance or sell the property. Here are some tips for dealing with older electrical systems. Firstly, have the system inspected. Have the electrical system inspected by a qualified electrician to identify any potential problems. Secondly, replace deteriorated wiring. Replace any wiring with deteriorated insulation. Thirdly, upgrade the grounding system. Upgrade the grounding system to ensure that it meets current safety standards. Fourthly, install a size. Install a size to protect against arc faults. Fifthly, replace the service panel. Replace the service panel if it is undersized or outdated. Sixthly, balance the load on shared neutral wires. Balance the load on shared neutral wires to prevent overloads. Seventhly, address aluminum wiring issues. Address any issues with aluminum wiring, such as loose connections or corrosion. Eighthly, install ground fault circuit interrupters, or GFCIs. Install GFCIs in areas where there is a risk of electric shock, such as bathrooms and kitchens. Ninthly, remove asbestos-containing materials. Remove any asbestos-containing materials by a qualified professional. Tenthly, bring the system up to code. Bring the electrical system up to code to ensure safety and compliance. When dealing with electrical problems in commercial buildings, several unique considerations and challenges arise compared to residential settings. Firstly, high voltage systems. Commercial buildings often use high voltage systems, such as 208/120 volts or 480/277 volts, which require specialized knowledge and equipment to work with safely. Secondly, complex wiring systems. Commercial buildings typically have more complex wiring systems with multiple circuits, panels, and distribution boards, making it more challenging to trace and troubleshoot electrical problems. Thirdly, larger electrical loads. Commercial buildings typically have larger electrical loads due to the use of heavy machinery, HVAC systems, and extensive lighting, which can lead to overloaded circuits and other electrical issues. Fourthly, three-phase power. Commercial buildings often use three-phase power, which requires a different set of knowledge and skills to work with compared to single-phase power. Fifthly, emergency power systems. Commercial buildings are often equipped with emergency power systems, such as generators and uninterruptible power supplies, or UPSs, which require regular maintenance and testing to ensure they function properly in the event of a power outage. Sixthly, compliance with codes and regulations. Commercial buildings must comply with a wide range of electrical codes and regulations, including the NEC, as well as local and state codes, which can be complex and difficult to navigate. Seventhly, tenant improvements. Commercial buildings often undergo tenant improvements, which can involve significant electrical work and require careful planning and coordination to avoid disrupting other tenants. Eighthly, data and communication cabling. Commercial buildings typically have extensive data and communication cabling, which must be installed and maintained properly to ensure reliable network connectivity. Ninthly, lighting systems. Commercial buildings often have complex lighting systems, including fluorescent, LED, and high-intensity discharge, or HID, fixtures, which require specialized knowledge to troubleshoot and repair. Tenthly, safety concerns. Electrical work in commercial buildings can be particularly dangerous due to the higher voltage systems and complex wiring, requiring strict adherence to safety protocols and the use of appropriate personal protective equipment, or PPE. Here are some specific considerations for troubleshooting electrical problems in commercial buildings. Firstly, identify the source of the problem. Start by identifying the source of the problem, whether it is a trip breaker, a faulty device, or a wiring issue. Secondly, use appropriate test equipment. Use appropriate test equipment such as multimeters, clamp meters, and circuit tracers to diagnose the problem accurately. Thirdly, follow lockout/tagout procedures. Follow lockout/tagout procedures to ensure that the power is disconnected before working on any electrical equipment. Fourthly, consult electrical schematics. Consult electrical schematics and diagrams to understand the wiring system and identify potential problems. Fifthly, coordinate with other trades. Coordinate with other trades such as HVAC technicians and plumbers to avoid conflicts and ensure that the electrical work is performed safely. Sixthly, document all work. Document all work performed, including the date, time, description of the problem, and the solution. Seventhly, use qualified personnel. Use qualified and experienced electricians to perform electrical work in commercial buildings. Eighthly, comply with codes and regulations. Comply with all applicable electrical codes and regulations. Ninthly, obtain necessary permits. Obtain any necessary permits before starting any electrical work. Tenthly, prioritize safety. Prioritize safety at all times when working with electricity. Let's talk about how to use an amp meter safely. An amp meter, also known as a clamp meter, is an essential tool for electricians and technicians to measure the current flowing through a conductor without having to interrupt the circuit. It is crucial to use an amp meter safely to avoid electrical shock, burns, and damage to the equipment. Here are some guidelines for using an amp meter safely. Firstly, use appropriate personal protective equipment or PPE. Wear appropriate PPE such as safety glasses, insulated gloves, and arc-rated clothing to protect yourself from electrical hazards. Secondly, inspect the amp meter. Before using the amp meter, inspect it for any signs of damage such as cracked cases, frayed wires, or loose connections. Do not use the amp meter if it is damaged. Thirdly, choose the correct amp meter. Choose an amp meter that is appropriate for the voltage and current levels you will be measuring. Make sure the amp meter is rated for the category of electrical system you are working on. Fourthly, understand the amp meter's functions. Understand the amp meter's functions and how to use them properly. Read the manufacturer's instructions carefully before using the amp meter. Fifthly, de-energize the circuit. Whenever possible, de-energize the circuit before taking measurements. This will eliminate the risk of electric shock. Sixthly, use the one-hand rule. When taking measurements on a live circuit, use the one-hand rule. Keep one hand in your pocket or behind your back to avoid creating a path for current to flow through your body. Seventhly, clamp the amp meter around a single conductor. Clamp the amp meter around a single conductor to measure the current flowing through it. Do not clamp the amp meter around multiple conductors or a cable containing multiple conductors. Eighthly, select the appropriate range. Select the appropriate range on the amp meter to get an accurate reading. If you are unsure of the current level, start with the highest range and then decrease it until you get a reading. Ninthly, avoid touching live parts. Avoid touching any live parts of the circuit or the amp meter while taking measurements. Tenthly, use caution in wet environments. Use caution when taking measurements in wet environments. Water can conduct electricity and increase the risk of electric shock. Here are some additional safety tips for using an amp meter. Firstly, never exceed the amp meter's maximum ratings. Secondly, do not use the amp meter in explosive atmospheres. Thirdly, do not use the amp meter to test for the presence of voltage. Fourthly, do not leave the amp meter unattended while it is connected to a circuit. Fifthly, turn off the amp meter when it is not in use. Sixthly, store the amp meter in a safe place. Seventhly, have the amp meter calibrated regularly. Eighthly, seek training on the safe use of amp meters. Ninthly, follow all applicable safety regulations. Tenthly, if in doubt, ask for help. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations and safety. Here are some relevant sections of the NEC that relate to the topics discussed. NEC Section 110.3 covers examination, identification, installation, and use of equipment. This section requires that electrical equipment be installed and used in accordance with the manufacturer's instructions and that it be suitable for the intended purpose. NEC Section 110.14 covers electrical connections. This section specifies the requirements for making electrical connections, including the use of approved connectors and proper torque. NEC Section 210.20 covers overcurrent protection. This section specifies the requirements for overcurrent protection, including the use of circuit breakers and fuses. NEC Section 210.21 covers the use of receptacles. This section specifies the requirements for the use of receptacles, including the number of receptacles required in different types of occupancies. NEC Section 210.23 covers permissible loads. This section specifies the permissible loads for branch circuits, including the maximum number of devices that can be connected to a circuit. NEC Section 215.3 covers overcurrent protection for feeders. This section specifies the requirements for overcurrent protection for feeders, which are the conductors that supply power from the service equipment to branch circuits. NEC Section 220 provides requirements for calculating branch circuit, feeder, and service loads. This is essential for determining the appropriate size of conductors and overcurrent protection. NEC Section 240 covers overcurrent protection. This is a comprehensive section detailing the requirements for circuit breakers and fuses, including selection and installation. NEC Section 250 covers grounding and bonding. This is a critical section for ensuring electrical safety by providing a low impedance path for fault current to return to the source. NEC Section 310.15 addresses ampacity of conductors. This section provides tables and guidelines for determining the allowable ampacity of conductors based on their size, insulation type, and installation conditions. The tables specify the maximum current that a conductor can carry safely without overheating. NEC Article 400 covers flexible cords and cables. This article specifies the requirements for flexible cords and cables, including their use, construction, and ampacity. Flexible cords and cables are commonly used to connect portable appliances and equipment to electrical outlets. NEC Article 408 covers switchboards and panel boards. This article provides requirements for switchboards and panel boards, including their construction, installation, and overcurrent protection. Switchboards and panel boards are used to distribute electrical power to various circuits within a building. NEC Article 430 covers motors, motor circuits, and controllers. This article provides requirements for motors, motor circuits, and controllers, including their overcurrent protection, disconnecting means, and control circuits. Motors are commonly used in commercial and industrial applications to power machinery and equipment. These are just a few examples of the many relevant sections of the NEC. It is essential to consult the NEC for complete and up-to-date information on electrical safety. Remember that electrical work should always be performed by qualified and experienced individuals who are familiar with the NEC and local electrical codes. Adhering to these codes and guidelines is crucial for ensuring the safety of people and property. Also remember to stay calm and explain the situation clearly. The person may or may not be understanding. Offer to help find a solution and document all findings.